Welcome to my presentation about anomaly detection in Scratch assignments. Scratch is a block-based programming language commonly used to introduce novices to the concepts of programming. In my bachelor's thesis, I introduced anomaly detection for Scratch to help teachers with debugging their students' code and giving feedback. The ICSI paper Finding Anomalies in Scratch Assignments sums up my work, and in this presentation I will introduce you to our initial approach as well as a recent enhancement which I describe in the paper for the student research competition. Imagine a small task. Move a sprite whenever the space key is pressed. The script on the left of the poster is obviously wrong. It's using a go to position block instead of a move steps block. The sprite is put to the same position instead of being moved. For us, it's quite easy to debug the script, but in a classroom scenario where teachers are probably not highly trained in software development, the activity of debugging is much more complex than just looking at one script. Teachers have to help many children solving the same programming task at once. This is where automated tools can help, especially this is where anomaly detection can help. The main idea of anomaly detection is to find patterns in the code that appear frequently. Rare deviations from these patterns, so-called violations, likely hint at bugs in the code. But how do we come from Scratch projects to patterns and violations? We need a representation of scripts that allows us to mine patterns. For this, I defined script models. Script models summarize the control flow of the individual scripts and are labeled with instructions. From these script models, we extract pairs of blocks where one block can precede the other in program execution. These pairs of blocks are called temporal properties. Block patterns are sets of temporal properties which occur frequently within a dataset. If in my dataset of solutions for this task there are many correct scripts, we will find the pattern representing the correct solution frequently. The temporal properties of the buggy script do not contain the move steps block. Anomaly detection will therefore yield a violation which directly hints at the missing block in this case. A violation that is reported is called anomaly. Our evaluation dataset consists of student solutions for 6 different tasks. The solutions were created by children aged 8 to 13 in programming sessions conducted by qualified teachers. We mined anomalies just like a teacher would, so separately for every task. The great thing is that no manual work is necessary, no writing of tests, no manual inspection of all programs. Overall, the majority of anomalies we inspected hinted at defective code. We manually classified 60 anomalies, 46 of which were defective, 4 were smelly, and 10 hinted at non-defective code. Now let's have a look at 2 examples from the cat task. The script at the bottom is an example of the right blocks assembled in the wrong order. The cat should be programmed to say "got you" only after touching the ball. A common generic linter would not be able to identify this bug, as using a say block before an if-then block is not a generic bug pattern. In contrast to that, the anomaly reports this project-specific bug. The red dotted transition indicates that the say for seconds block usually comes after the if-then block. This violation is useful for the student who can fix the code, and the teacher can talk about script flow in class. The second anomaly, shown on top of the wrong order anomaly, shows an example of smelly code which was located in a sprite which was not supposed to be programmed and therefore has no influence on the correctness of the program. My initial approach abstracts away from the actor, so the sprite or background, of a script, and the anomalies are actor agnostic. I implemented a context-sensitive anomaly detection variant which I call actor-specific anomaly detection. I group all the scripts by the purpose of their actor. I mined actor-specific anomalies for the cat task and compared the results with the actor-agnostic anomalies. I want to point out that one very beneficial change that comes with the actor-specific anomalies is that the actor-specific approach yields only anomalies that hint at code in relevant actors. All of the resulting anomalies hinted at code in the cat, therefore focusing anomaly detection at the relevant parts of the programs. To sum up, anomaly detection in Scratch is a useful approach to help teachers with assessing their students' code. This research field is still young, and the first step to improve the initial approach by mining actor-specific anomalies yielded promising results that are worth investigating in further experiments.